Just now, we introduced several metrics. Next, we will see how to compute the gradients of the metrics. After that, we can apply the gradients to gradient ascent algorithms to find optimal policies. This is what I said just now. Before diving into the details, I want to emphasize that calculating the gradients of these metrics is the most complicated part of policy gradient methods. Why is it complicated? There are two main reasons. First, we have multiple different metrics, like v pi bar, r pi bar, and v pi bar 0. V pi bar 0 is a special case of v pi bar where the distribution of states is independent of the policy pi. Second, as we mentioned earlier, we need to distinguish between discounted and undiscounted cases. If we combine different objective functions and different discounted cases, each scenario requires a different way of calculating the gradient. This is why this part is very complicated. As a result, we are not able to discuss the details in this lecture. If you're interested, you can see my book for details. I will just give a brief introduction in this lecture. Here, I directly present the gradient expression without proof. J is the objective function, and its gradient with respect to theta is given on the right-hand side. Let's examine closely what's on the right-hand side. First, we sum over each state S. Each state has a weight or probability. For each state S, we choose an action, and then we sum over these terms. What do we add? We add the gradient of the policy and the action value Q pi SA, which is the action value of SA. This equation is very important and deserves special attention. First, J theta can be V pi bar, R pi bar, or V pi bar 0. Second, there are three cases for this equality: exact equality, approximation, and proportional to. Third, the distribution eta varies depending on the metric. Nevertheless, although the details differ, the general expressions of the gradients for all these cases are similar, so we can represent them using this unified equation. I will not explain how to obtain this equation since the derivation is very complex. If you are interested, you can refer to my book for details. For most readers, knowing this equation without knowing the proof is already sufficient. Now let us analyze the gradient I just presented. The most important property is that this gradient can be written in the following expression. We can remove all the summations and re-express it as an expectation. Here, SA is a random variable. S follows the distribution eta and A follows the distribution of pi. Next, we answer two questions about this expression. First, why do we need to rewrite it in this expression? Second, how can we obtain this expression? First, let's see why we need such an expression. I believe some of you might already realize the reason. The reason is that it is the true gradient, which would be better expressed as an expectation. While we do not know the true gradient, we can approximate it with a stochastic gradient based on sampling. Later, we will see the details. This is also the basic idea behind stochastic gradient descent or ascent. This is why this expression is very important. Second, let's see how we can obtain this expression. Actually, it's quite simple. It's important to note that there is a term involving ln pi. What is ln pi? It is the natural logarithm of pi, where pi is the policy function. The natural logarithm is sometimes written as log, but to indicate that the base is the natural number, I write it as ln. What property does ln pi have? If we take the gradient of ln pi, it equals the gradient of pi divided by pi. Why is this valid? For example, if we take the derivative of ln x with respect to x, the result is 1 over x. If we have ln fx, where fx corresponds to our pi, the gradient of ln fx contains 1 over fx and then the gradient of fx. This is why this expression is valid. Now, if we multiply both sides of this equation by pi and then swap the sides, we get this expression. The gradient of pi equals pi times the gradient of ln pi. Substitute this expression into the gradient expression we gave earlier. Originally, the gradient of pi was there, but now we will replace it with pi times the gradient of ln pi. Why do we make this substitution? It is because it allows us to express the equation in the form of an expectation. Let's see how. First, We remove the summation and rewrite it as an expectation. The variable s here follows the distribution of d. Next, we rewrite this summation in expectation as well. So, the variable a here follows the distribution of pi. This gives us the desired expression. We may omit the subscripts below and use this expression. After introducing this gradient, let's see some additional explanation. The first is something you may have already noticed. When we put pi inside the loin function, pi must be greater than 0. Why is that? If the horizontal axis is x and the vertical axis is loin x, then x must be greater than 0. If x equals 0, then the logarithm function is invalid. Previously, we introduced policies like greedy or deterministic policies, where the value of pi for some actions may be 0. However, that should be avoided now. How do we ensure that all pi values for all actions are greater than 0? We can use the softmax function. What does softmax do? It normalizes values, mapping them from the range of -infinity to +infinity into the range between 0 and 1. Moreover, the mapping cannot equal exactly 0 or 1. Specifically, let's look at this example. Suppose we have a set of values x1 through xn. If we put them into this function, the numerator will be exi, and the denominator will be the sum of exi. This gives us the value zi. In fact, this is a function z equals fx, where the values of x can range from -infinity to +infinity, and the resulting z will always be a number between 0 and 1. Furthermore, the sum of all the z values will always be equal to 1. Now, let's come back to pi. Since pi is a function, to ensure that pi is greater than 0 for every action A, we force that it must satisfy this specific structure, EH divided by the sum of EH, where h is another function. This h is similar to the feature vector that we discussed earlier in value function approximation. How do we choose this h function? Nowadays we use neural networks. This means that if I have a neural network with parameters theta and input s, the network can directly output pi a 1 theta through pi a 5 theta, for example, if there are 5 actions. The output layer of the network must use softmax, and then all these outputs will be between 0 and 1, and their sum will be equal to 1. Since pi is greater than 0 for every action A, this policy is stochastic and hence exploratory. In the next lecture, we will introduce the deterministic policy gradient methods. At that point, we won't need this condition anymore. The advantage of the deterministic policy gradient methods will be discussed later.